In this video, we're going to take a look at solving trig equations involving double angle formulae. So for this video here, we're going to take a look then at 3 practice questions for solving trig equations involving double angle formulae. There's not really much to introduce here or go over, but to quickly recap then, we have the results then for sine 2x and cos 2x. So for sine 2x, nice and straightforward, this is simply 2 sine x cos x, so hopefully nice and easy to remember. Now for cos 2x, the easiest way to go about this is to just remember cos squared x minus sine squared x for cos 2x. And from here, we can derive 2 further results then. So using sine squared x plus cos squared x equals 1. What I can do here is rearrange here to make sine squared x and cos squared x a subject, and then substitute those into cos squared x here and sine squared x. So we do those individually. We obtain 2 further results then. We obtain 2 cos squared x minus 1, and then finally 1 minus 2 sine squared x. So, like I said, there's not really much to go over here. For this video, I'm going to use the cast diagram method to solve these trig equations. Now, you don't have to use a cast diagram if you prefer, say, a graphical method. That's absolutely fine as well. I will use a cast diagram as I go through this video. If you're not familiar with a cast diagram and how we can use that to solve a trig equation, then go back and check the first year material then on trigonometry. We have a full video on using a cast diagram. Other than that though, I think that's everything that we need here to get started. So let's begin now with question 1. Starting off with question 1 then, where it says solve for x being between 0 and 540 degrees the equation cos x equals sine 2x. So we're using double angle formula here to help solve these trig equations. So what I can see then is on the right hand side we have sine 2x. We can use the double angle result then for sine here. Obviously we can't do anything with the left hand side, that is simply cos x. So on the left hand side we have cos x. On the right hand side then, rather than writing this as sine 2x, we can write this as 2 sine x cos x. So 2 sine x cos x. So from here, what I want to do is set the equation here equal to 0. Okay, so what I'm going to do then is subtract cos x of both sides. So we get 2 sine x cos x minus cos x then is equal to 0. Okay, and from here now what I can do is factor out a cosine x. So we get cosine x bracket 2 sine x. So 2 sine x minus 1, and this is all equal to 0. And from here now we get 2 equations. I've got cos x equals 0. We get cos x equals 0. We also got this equation here. So I've got 2 sine x minus 1 equals 0. Add 1 to both sides, so we get 2 sine x equals 1. And then divide through by 2, so we get sine x equals a half. So sine x equals a half there. So from here now, I get x here by taking cos inverse of both sides. So x equal to cos inverse of 0. So you put this into your calculator here. Obviously make sure that you're working in degrees mode rather than radians mode within your calculator. And what I get then is 90 degrees here. So I get 90 degrees there. Now, it's up to you what method you use. Like I mentioned in the introduction, I'm going to use a cast diagram here as I go through solving these trig equations. If I quickly draw up my cast diagram here at the top, it doesn't need to be perfect. Let's say it looks something like this. I've got C, A, S, and T. So that's for tan there. So working with cosine here, so where is cosine positive? Well, we've got this quadrant here because all trigonometric functions are positive in this quadrant. I've got this angle here, which would actually be the 90 degrees here. Clearly that is not 90 degrees, but we'll go with it. So that's 90 degrees there. And cosine is also positive in this quadrant here. Okay, so this quadrant here. So what we're looking for is if we start here on what would be the x-axis and we go around, so we touch this line here, what is the angle that is formed? Well, that would be 360 degrees minus this angle here, which is also 90 degrees. So that's also 90 degrees. So in that case then 360 minus 90, and that gives me 270 degrees there. Okay, my principal solutions then are 90 degrees and 270 degrees for this equation here. We also got sine x here equals a half. So x here is given by taking sine inverse of both sides. So x equal to sine inverse, or arc sine, whichever you prefer, of a half. Again, just put this into your calculator here. Again, making sure that you're in degrees rather than radians. And what you'll get here is 30 degrees. So I get 30 degrees there. And again, if we just consider a cast diagram here for the other principal solution. Again, C, A, S, and T. Well, sine is positive in this quadrant here. So that would be 30 degrees. And then sine is also positive in this quadrant here. Okay. So this angle here would also be 30 degrees. But what we're looking for, again, is going from the x-axis here, round and round and round until we touch this line here. And what is this angle that is formed? Well, that would be 180 degrees minus this angle here, which is 30. That would be 180 minus 30, giving me 150 degrees. Now, we're not quite done here because notice the domain for x is from 0 to 540 degrees. So what other solutions can we obtain here? Well, we know that sine and cosine are both periodic every 360 degrees. So let's consider what happens then if we add, I should say, 360 degrees to these solutions here. Okay. So 90 degrees plus 360, that would give me 450 degrees. So other solutions. So other solutions here, we obtain 90 plus 360, which gives me 450 degrees. So 450 degrees there. I've got 270 degrees here. Now, if I add 360 to that, we're going to fall outside of this domain here. That would be too large. Okay, it'd be greater than 540, so therefore we would reject that solution. We then got these two solutions here. So if we now add 360 to these, what do we get? Well, 30 plus 360, that gives me 390. So that falls within the domain then. And then finally 150 plus 360, that gives me 510. So again, we can accept that solution. Okay, so that's 510 degrees. There we go. Obviously, if I now add 360 to any of these here, we would fall outside of the domain here for x. It would be greater than 540. So we would reject those solutions. So therefore then, we've now found the full set of solutions here. So let's just write down the full set of solutions. So therefore, x is equal. So x is equal then to 30 degrees. Let's try and do it in order. We've got 90 degrees. We have 150 degrees. We've also got 270 degrees. We've got 390. I'm hoping I just have about enough room here. I've got 450 degrees. 450 degrees. And then finally, 510 degrees there. 510 degrees. Perfect, there we go. Just about enough room. So there we have it. So that is the solution there to question 1. Moving on to question 2, then we want to solve for x being between 0 and 2 pi cos 2x minus 3 equals 1 minus 5 sine x. So to start off with here, I'm just going to write down this original trig equation. So we have cos 2x minus 3 is equal to 1 minus 5 sine x. So obviously we need to solve this trig equation here, and we're using the double angle formulae where possible. I've got cos 2x here, and we know that cos 2x is equal to cos squared x minus sine squared x. Okay. Now, when I substitute this in here, this isn't really going to work because what I want is an equation that's just in terms of one trigonometric function. So given that we're working with cos and sine here, we want this to be in terms of just sine or cos here. And given that this is minus 5 sine x here on the right hand side, that would suggest here that we need this to be in terms of just sine. So we also know here by using sine squared x plus cos squared x equals 1. What I can do here is substitute in for cos squared x being equal to 1 minus sine squared x into cos squared x here. We can obtain then 1 minus 2 sine squared x. Okay, by substituting this here into the original equation then for cos 2x. Okay, so I just rearrange this here to be cos squared x is 1 minus sine squared x. And then we substitute that into this here. Okay, and that gives us 1 minus 2 sine squared x. What I'm going to do now is substitute cos 2x here for the equation here, 1 minus 2 sine squared x. So 1 minus 2 sine squared x minus 3 is equal to 1 minus 5 sine x. So from here, what I want to do now is get this quadratic equation equal to 0. So I'm going to make this positive here and add this to both sides. I've also got 1 minus 3 here, so I've got minus 2 is equal then to 2 sine squared x. I've got minus 5 sine x. I've also got the plus 1 here. So if we want this equal to 0, I now need to add 2 to both sides. So therefore, 2 sine squared x minus 5 sine x. We've got 1 plus a 2 there, gives me plus 3. And this is equal to 0. Okay. So from here now, what I want to do is attempt to factorize this quadratic equation here. It's up to you whether you replace this as, for example, say 2y squared minus 5y plus 3 equals 0. That's fine as well. I don't feel like it's necessary here, but if you want to do that, that's absolutely fine. What you get here if you factorize this is 2 sine x minus 3, the first bracket, and then for the second bracket here we get sine x minus 1. Like so, and this is equal to 0. So from here then we get two equations. So from this bracket we get sine x equals 3 over 2. So sine x equals 3 over 2. And then from this bracket here, we get sine x equals 1. Okay. So what we need to do now is solve these two individual equations here. So if I go to solve this first equation here, well, we take sine inverse of both sides. So I get x equal to sine inverse of 3 over 2. However, if you go to put that into your calculator here, you'll notice that you get an error. Okay, so we can't find the value of x such that sine x equals 3 over 2. So therefore, we just say that there are no solutions here for this first equation. Or we can just kind of cross it out here like so. We've then got sine x equals 1, which we can solve. So x equal to sine inverse of 1. And don't forget here, we are working in radians, so we're working between 0 and 2 pi here for x. So x equal to sine inverse of 1. That means that x equal then 2 pi over 2. Okay. And if we just quickly think about a cast diagram here to obtain the full set of solutions then. I'll quickly draw my cast diagram here. We've got C, A, S, and T. Well, we're working with sine here, so where is sine positive? Well, sine is positive in this quadrant here. And sine is also positive in this quadrant here. Now, you might notice straight away, the angle that we obtained here for x equals pi over 2. If I say this is pi over 2 here, which it clearly isn't because pi over 2 is 90 degrees, the angle there, clearly not 90 degrees. But if we say it's pi over 2 there, so pi over 2 radians, then my next solution comes from pi, because that's 180 degrees, minus this angle here, which is also pi over 2. And pi minus pi over 2 would just give us pi over 2. Okay. And the next solution then would come from pi over 2 plus 2 pi. But clearly that would take us outside of the domain here. It would be greater than 2 pi, so therefore we would omit that solution. So in that case then, the only solution here for this equation is x equals pi over 2. So therefore, only solution. So the only solution here is x equals pi over 2. Okay. And there we have it. So that's the solution there to question 2. And finally then, if we take a look now at the very last question here, question 3, where we've got two parts of this question. Let's begin with part A. Now for part A, it says by writing cos 3 theta as cos of 2 theta plus theta, show that cos 3 theta is equal to 4 cos cube theta minus 3 cos theta. So for part A then, very typical kind of opening part to an exam style question on trigonometry here. So we need to express this as cos of 2 theta plus theta like it mentions here, which I'll do underneath just so we've got a bit of extra room. So cos of 2 theta plus theta. Now, before we do this, what we need then is the addition formula for cosine here. So I need cos of A plus B, where in this case, A would be 2 theta and B would simply be theta. So this result is given in the formula, but you don't have to worry about memorizing this here. So this is given as cos A cos B. So cos A cos B minus sine A sine B. Okay, so in that case then going back to cos of 2 theta plus theta, what we've got here is cos 2 theta. So cos 2 theta times cos theta minus sine 2 theta times sine theta. Okay, so just using this result here. Now what I notice straight away is we have cos 2 theta and sine 2 theta, so we need to use the double angle formulae here. Now for cos 2 theta, what am I going to use here? So for cos 2 theta, what I'm going to use here is 2 cos squared theta. So 2 cos squared theta minus 1. And the reason that I'm using that is because we need for work cos cube theta here. Well, clearly if I substitute this in then for cos 2 theta and I times that by cos theta, we're going to obtain some term in cos cube theta. Okay, it'd be a multiple of cos cube theta. So replacing cos 2 theta then with the right hand side here, we get 2 cos squared theta minus 1, and let me just put this in a bracket here just to make it clear. We times that then by cos theta. We've also got minus sine 2 theta here. So in that case then we know that sine 2 theta, nice and straightforward here, is simply 2 sine theta cos theta. So I've got minus 2 sine theta. So minus 2 sine theta cos theta. And don't forget the sine theta here at the very end. So minus 2 sine theta cos theta sine theta. Okay. So from here now we just need to start cleaning this up. And this is for cos 3 theta. Okay. Well, I've got 2 cos squared theta and I times that by cos theta. That gives me 2 cos cube theta. So 2 cos cube theta there. We've also got minus 1 times cos theta, so that's minus cos theta. So here now we've got minus 2 sine theta cos theta sine theta. So if we simplify that, it's simply minus 2 sine squared theta times cos theta. Okay. If we notice here, for the right hand side, it shows 4 cos cube theta minus 3 cos theta. So there's no terms involving sine here on the right hand side. So obviously we need to get rid of this sine squared theta here, or this minus 2 sine squared theta here. So to do that, we're going to use another trig identity here. So we're going to use sine squared theta plus cos squared theta equals 1. I know then that I can make sine squared theta the subject here. So if sine squared theta is the subject, we get 1 minus cos squared theta here. And what I can do now is replace this sine squared theta here with 1 minus cos squared theta. So obviously this will just remain as it is. So 2 cos cube theta minus cos theta. We now got minus 2 sine squared theta. So the sine squared theta, like we said, we replace that with 1 minus cos squared theta. And because we times through by cos theta, what I've actually got here then is minus 2 cos theta times by 1 minus cos squared theta. Like so. Okay. So we're nearly done here. If we just expand this bracket here then, obviously this just remains as it is. So 2 cos cube theta minus cos theta And then we've got this bracket here. So minus 2 cos theta times 1. That would simply be minus 2 cos theta. And then we've got minus 2 cos theta times by negative cos squared theta here. So a minus times a minus becomes a positive number or a positive term. So this would be plus 2. And it's 2 cos theta times negative cos squared theta. Or let me just try that again. So minus 2 cos theta times minus cos squared theta. So like we said, it becomes positive, and it will be cos cubed theta then. Okay. So there we have it. And we're nearly done now. All we need to do here to finish with is collect like terms. Well, I've got 2 cos cubed theta plus 2 cos cubed theta. That gives me the 4 cos cubed theta there that we require. Perfect. So 4 cos cubed theta there. We've also got minus cos theta, minus 2 cos theta. So there we go, we get minus 3 cos theta. So minus 3 cos theta there. And that is for cos 3 theta. That's equal to exactly what we needed there as required. Okay. So there we have it. So that is the solution there to part A. So now let's just clear the screen here just so we can have a go at part B. We just take a look then at part B where it says hence with y solve for theta being between 0 and pi. 12 cos cubed theta equals 9 cos theta plus 3 over 2. So to start off with, I'm just going to write down the original trig equation. So for part B then we have 12 cos cubed theta. And this is equal to 9 cos theta plus 3 over 2. Okay. Now, because it says hence with y, that would suggest that we're going to use our answer in part A to help us answer part B. And what I also noticed straight away is that if I subtract 9 cos theta off both sides here, on my left-hand side, then we get something that looks pretty close to this here. Okay. If we do that then, we get 12 cos cubed theta. So 12 cos cubed theta minus 9 cos theta. And this is equal to 3 over 2. Okay. So from here, like we said, then this looks pretty close now to what we have here on the right-hand side. In fact, it's just 3 lots of this. So what I've got then is 3 lots of 4 cos cubed theta minus 3 cos theta is equal to 3 over 2. Okay. So if this here is equal to cos 3 theta, then what I've got is 3 cos 3 theta is equal to 3 over 2. Okay. Well, here we just want cos 3 theta on its own, so I'm going to divide both sides by 3. So we get cos 3 theta is equal then, well, 3 over 2 divided by 3, that's equal to a half. So cos 3 theta is equal to a half. And before we take cos inverse here of both sides, just notice that the argument here of my trigonometric function isn't just theta, it's actually 3 theta here, so we need to take that into account then for the domain here. So we're working for 3 theta, so 0, 3 theta, and this would be pi times by 3, so we get 3 pi there. Okay. So from here then, like we said, now we can take cos inverse of both sides. So I do that over here. Then 3 theta is equal to cos inverse of a half. So cos inverse of a half, which is equal to pi over 3. Okay. Obviously, just to ensure that you're working in radians here, working between 0 and 3 pi. So we get pi over 3 there. So let's just consider a cast diagram to obtain the full set of solutions here. I draw my quadrants on here, like so. We've got C, A, S, and then finally T. So where is cosine positive? We're working with cosine here, so cosine will be positive in this quadrant here. So this angle would be pi over 3 that we've just found here. So we've got pi over 3, and cosine is also positive in this quadrant here, like so. We've got this angle here, which would also be pi over 3. But what we're really looking for is the angle that's formed going from what would be my x-axis here, all the way around until we meet this line here. Okay, so what's the angle that's formed? Well, that would simply be 2 pi radians minus pi over 3. So in that case then, 2 pi minus pi over 3, that would give me 5 pi over 3 there. Okay, we get 5 pi over 3. So that would be our principal solutions there. So the solutions between 0 and 2 pi radians. Okay, now notice here the domain is from 0 to 3 pi. So what we need to consider now is if we add 2 pi to these solutions here, would we still be within this domain here? If I've got pi over 3 and I add 2 pi to that, I get 7 pi over 3, which is still within the domain here. Okay, so next solution. So my next solution here is given from, so we're solving for theta here. This is 3 theta actually. That's going to be 2 pi plus pi over 3. What that gives us then is 7 pi over 3. Okay, so we get 7 pi over 3 there. So what I've got now is the full set of solutions here for 3 theta. I can add 2 pi to this, but if I do, it falls outside of this domain here, so we would omit that solution. So we've got all the solutions then for 3 theta between 0 and 3 pi. So here then, we've got 3 theta is equal to, I've got pi over 3. We've also got 5 pi over 3. And then finally, we've got 7 pi over 3. Okay. So 7 pi over 3. But remember, we're not solving for 3 theta here. Okay, these are in terms of 3 theta. We just want theta on its own. So to do that, nice and easy, we just divide both sides by 3. So divide 3 by 3 here. Do the same with the solutions here. And in that case then, we get theta here is equal. Well, if we divide 3 by 3, that's supposed to be a 3, believe it or not. So we divide 3 by 3, it's the same as times in by a third. So we've got pi over 3, and I divide that by 3, I get pi over 9. Pi over 9 there. 5 pi over 3, again, times through by 1 over 3, so I get 5 pi over 9. And then finally, 7 pi over 3, if I times through by 1 over 3, I get 7 pi over 9. Okay, and there we have it. So that is the full set of solutions there. And that gives us the solution to the very last question, question 3. And that brings the end of this video on solving trig equations involving double angle formulae.